Welcome back. We're in Giancoli Acceleration, which is Chapter 2, Questions and Problems, Set Number 2, Problem Number 2. A car is traveling at 90 kilometers an hour, strikes a tree. The front end of the car compresses, and the driver comes to rest after traveling an additional 0.8 meters from the car compressing there. What's the average acceleration of the driver during the collision? Express the answer in terms of g's, where 1 g is equal to 9.8 meters per second squared. Okay, first and foremost, when I read this, the first thing that strikes out to me, is that this is a non-standard unit. We need to change this into what's called SI units, or Standard International Units, which are meters and seconds, like this, but not the squared there, because that's an acceleration. This one's not an acceleration. It's a speed in this case, although we could put a direction to it and make it into velocity. So I make a big note to myself, and I'm going to go do that, but I want to draw a picture first to make sure that we know what's going on here. So first we have a car, so we draw a car. Our skills of drawing a car from the last problem are increasing here. Well, there's like a much bigger back end of that car. That's not so useful for this problem here. You could probably do it differently. And the car is crashing into this tree here. So here's my crude tree. But it's crashing in there, so the car was going this direction. And I'm going to go ahead and draw it again where the car is done crashing into the tree. And I'm going to assume that this is a big tree. So here's like the before and after, before, after. And I'm going to assume it's a big tree, so the tree is not going to like fall over or break or even move at all. Now that's not really true, it's going to bend and such, but we're going to ignore that bit for the purpose of this problem, otherwise it becomes a very, very complex problem. And we said that the front end is going to crumple, so I'm going to try to show that it's crumpled there. And hopefully his passenger container is more or less unaffected. And I drew my front end on the first picture too short, so it almost looks like the same length. That was a poor move, Mr. Wishway. Yes, I learned from my mistakes. That's why I made that mistake, is so you can learn from it. Okay, going on here, we know that the original velocity, v naught, was 90 kilometers an hour, but I don't like that because it's a non-standard unit there. So we're going to have problems with that. We're going to have problems when we try to get it to an acceleration of meters per second squared. We won't be in meters and seconds. We'll be in kilometers and hours, and that's different. So let's go and let's transform that first and foremost. 90 kilometers per every 1 hour is another way to write that. So let's go set up some dimensional analysis, some factors here, so we can get that from kilometers into meters. So let's do that first. I'm going to go ahead and put kilometers down here and meters up there because I know how many meters are in a kilometer. There's 1,000. Kilo means 1,000, or is kind of short for 1,000. When I go and do that, now kilometers and kilometers cancel out, and now I'm in meters per hour, which is getting us closer, but we're not there yet. So let's get hours into seconds. Well, if I put hours up there, it'll cancel out, and I know how many minutes are in an hour off the top of my head. I actually know how many seconds are in an hour, but I'm assuming you don't, so I won't use that. But it's useful when you know things like that. Now we're in meters per minute, which again is getting us closer there, but not there yet. If I put minute on the top, now I can cancel that out, but it would only work if I know how many seconds are in a minute, and sure enough, pretty much everybody knows that one who has graduated elementary school, hopefully. And now we can go, okay, now this is in meters per second. So if I just do all this math here, multiplying these fractions, then I will have it in meters per second. Yay! So meters per, oh gosh, that's bad, meters per second. And now I grab my handy dandy calculator. I'm multiplying the numerators, 90 times 1,000, which I don't need to do in the calculator, and then divide by all the denominators multiplied. Now, when you're doing this in your calculator, you probably want to put parentheses around the denominator there. And 60 times 60, you can do that in your head. 6 times 6 is 36, and 10 times 10 is 100. So we got 36 with 2 zeros after it, 3,600. And that's how I knew how many seconds were in an hour, because I've done this calculation before. And so that's 25 meters per second. Cool. Great. So we know this is equal to V naught. Great. It comes to rest after traveling 0.8 meters, and I go and I label that as a change in position as 0.8 meters. So I'm trying to list out all the things that I know and things that I don't know. I want to figure out how many G's that is. So I ultimately want to figure out my acceleration. From my acceleration, I can compare that to what 1G is 9.8 meters per second squared. So how many groups of those will it be? Okay, great. So we basically just have, when we also know the ending velocity was 0. So let's go to our handy dandy equations and see which one we can use. Well, we got delta x is equal to 1/2 at squared plus v naught t. And I'm thinking about this whether I write it down or in my head, either way. I got delta x here, I know that. I got a, I don't know that. T, I don't know that. V naught, I do know. And t, I still don't know. Okay, so I got two unknowns here, so I have two unknowns in this one. Let's try the v is equal to at plus v naught. And here I have v, I know that. A, I don't know. T, I don't know. V naught, I don't know. So here I have two unknowns. So again, just like in the last problem, algebra can solve this. Algebra can combine these things, or we can combine these things with algebra, and we can get a third equation here, which isn't anything new, but instead the algebraic combination between these, and that's equal to v squared is equal to v naught squared plus 2a delta x. So let's go through this one. We know v, we know v naught, we know a, or we don't know a, but we're trying to solve for that, that's fine. And we know delta x. So here, let's go ahead and use this and solve for a, and that'll make our lives way easier. So I have v squared, and I'll move the v naught over to the other side, so subtract by v naught on both sides, is now equal to 2a delta x. And if you can do this all in one step, better for you. Divide by 2 times delta x on both sides there. So now I'm going to have v squared minus v naught squared, and divide by that 2 and the delta x there, and now I have an equation for just a, using the variables that I do know. Great! Now it's pretty simple because I can just go plug that stuff in. I know the ending velocity was 0 squared minus the beginning was 25. That's in meters per second. Notice that that's going to make our calculations way easier here, times 0.8 in the denominator there. So now we just grab our handy dandy calculators and we go to town. 25 squared divided by that stuff down there, and I get negative 390.625. I'm going to put a unit on that, so it's kind of like almost final answer here. Meters per second squared, and is my acceleration. Now I'm going to move that over. Good thing I'm electronic here, because I'm going to move that thing over so my equal sign is in line there. So I didn't plan that out too well. Okay, so first you might say, why is it negative? Did I expect it to be negative? Well, let's look back up at our problem here. If we can see which way our velocity is going to the right, and at the beginning it's going to the right, and then at the end it's not going anywhere, so there is no velocity. And so technically the length of this arrow is just a 0 length here, so I guess there's not actually an arrow there. But the only way to get from a velocity pointing to the right to a velocity that now is not pointing to the right, it's not pointing anywhere, is that it must be, while it's crashing, accelerating the opposite way. The velocity vector itself must be getting bigger in the negative direction. Oh, well, that means that it's going to be accelerating to the left here, and to the left we're going to assume is positive. Now, at the beginning of the problem, I didn't actually define that it's positive to the right and negative to the left, but we're always going to assume that the Cartesian coordinate plane that we normally use in math class, or we most commonly use in math class, that we're going to be using that unless we stated otherwise. So it's a okay assumption to do that. So the negative acceleration shouldn't be a problem. All right, now it asks for this acceleration in terms of numbers of g's. And so it said that a g was 9.8 meters per second squared. So I'm going to go ahead and I'm going to take our acceleration. I'm going to divide it by what the standard g is, and that will give me the number of g's, or the amounts of groups of g's. You could imagine if the acceleration was exactly 9.8, you'd have 1 1g. And if it was 19.6, which is double that of 9.8, then you'd have 2g's. And so if I just take whatever I have here, my acceleration, divided by g's, I'll get the number of g's. Now, it'll be negative, but again, that's just pointing to the left. So I take my 390.625 and divide it by 9.8, and I get 39.86. 39.86. And that's number of g's. Cool. And so that means that, hey, if you're just standing there, or sorry, not if you're just standing there, if you're free falling, if you're just walk off of the edge of a building or something like that, don't do that. Or if you drop something, that thing would be experiencing an acceleration of 9.8, acceleration due to just g, gravity. That's why we label it lowercase g. Well, this is accelerating almost 40 times more than what gravity accelerates things at. And when you drop things, they can get going pretty darn fast because this acceleration is actually fairly large. And so this, 40 times that, is even larger. All right, that's it. Have a wonderful day. See you. Bye.